heavy, black like a stone, but somehow different. Part of its surface shines with a dull silver glow. If someone had picked this up 5,000 years ago, what would they have thought it was? Today, iron feels ordinary. It is in our buildings, our cars, our kitchen knives, and even the blood moving through our bodies. But the first iron humans ever handled did not come from a mine. This story is not only about the first person who touched iron. It is about the long journey from finding a rare metal to recognizing its ores, controlling the right conditions, and producing useful amounts again and again. It is the story of how a discovery became a technology. Around 5,000 years ago, people in Egypt were already working iron, but they had not yet established a reliable way to produce it from iron or in large quantities. So where did that iron come from? The answer was not beneath the ground. It was above it. Our first clue is a meteorite that crossed the night sky and fell to Earth. In northern Egypt lies an archaeological site called Gerzeh. 9 small, tube-shaped beads were found in 2 graves there. They date to around 3200 BCE. At first glance, they look like tiny, rusted tubes, but they had been placed in a necklace beside gold, lapis lazuli, and carnelian. Iron was not being treated as an everyday material. It appears to have been something rare and special. The question was what kind of iron these beads were made from. Iron rusts badly over thousands of years. Studying only the surface cannot easily reveal the original composition of the metal or how an ancient craftsperson shaped it. Researchers used X-rays and neutrons to examine the beads without destroying them. They found a high concentration of nickel alongside the iron, a chemical signature consistent with meteoritic iron. And the craftsperson had done much more than drill a hole through a fallen lump of metal. The meteoritic iron had been hammered repeatedly into a thin sheet, then rolled into a tiny tube. That was not easy. Meteoric iron can vary from one area of a meteorite to another. Hammer it too hard while it is cold, and it may crack. Heat it too much, and it still may not behave as expected. Through repeated failure, ancient metalworkers must have learned how heat and force change the material. In other words, humans were forging iron from the sky long before they learned to smelt iron from ore. That is our first major clue. But there is no evidence that knowing meteoritic iron directly led to iron smelting. Working metal from meteorites and extracting iron from terrestrial or should be treated as 2 separate histories, at least at first. About 1900 years after the Gerzeh beads, an iron-bladed dagger was placed in the tomb of King Tutankhamun in the 14th century BCE. It is a beautiful weapon with a golden handle and sheath. When scientists examined the blade with X-ray fluorescence, its proportions of nickel and cobalt matched the characteristic pattern found in iron meteorites. Iron was still rare enough to be buried with a king. Egypt already had bronze tools and weapons. Iron was not automatically superior simply because it was iron. Metal from the sky is limited. You cannot collect the same amount or quality whenever you need it. Knowing how to forge meteoritic iron was not enough to begin the Iron Age. Perhaps someone who knew meteoritic iron looked at a red stone on the ground and wondered whether it also contained metal. It is a simple and appealing story, but no surviving evidence proves that this is what happened. Red minerals rich in iron had been used as pigments for a very long time. Humans knew iron ore first as a stone that produced red and yellow colors, not as the raw material for metal. Now place iron ore in an ordinary campfire. When the flames die, what remains is mostly a heated stone. A convenient lump of silver metal does not simply roll out of the ashes. In most iron ores, iron is tightly bonded to oxygen. Heating the ore is not enough. The oxygen must also be removed. That chemical change is called reduction. There is another problem. Pure iron melts at about 1,538 degrees Celsius. The earliest iron furnaces did not become hot enough to melt the iron itself. So how could people make iron without melting it? The answer required charcoal, a furnace, and a continuous supply of air. By the time experiments with iron began, humans already knew how to work copper and bronze. They knew how to crush or heat it with charcoal and use a furnace to separate metal from stone. Copper smelting furnaces can also produce slag rich in iron. Metal workers would have seen that different ores, furnace temperatures, amounts of fuel, and flows of air produce different results. But we cannot say that iron smelting was invented in one straight step from copper smelting. Some equipment and knowledge could be shared, but iron presented its own difficulties. The important point is that no lone genius had to imagine the entire process at once. Mining, charcoal making, furnace building, air blowing, and forging already existed. Over time, those skills could be combined in new ways. What follows is an evidence-based possibility, not a confirmed scene. During high-temperature work, such as copper smelting or pottery firing, an iron-bearing mineral may occasionally have been reduced by accident, producing tiny particles of metal. But archaeologists have not found a single workshop that proves this was the exact path of invention. What we can say with confidence is that one accidental particle could never create an Iron Age. People had to adjust the ore, the charcoal, the shape of the furnace, and the flow of air until success could be repeated. Crushed iron, ore, and charcoal are loaded into a furnace. Then air is forced inside, often with bellows, and the flow must continue. If the goal were only a larger flame, there would be no reason for such careful work. As charcoal burns, it creates carbon monoxide inside the furnace. That gas pulls oxygen away from the iron oxide. What remains gradually becomes tiny particles of metallic iron. The temperature is not the same everywhere inside the furnace. It is extremely hot near the tuyere, where the air enters, and cooler farther away. The size of the ore pieces and their ratio to charcoal also change the reaction. Too little air, and neither the heat nor the reaction is sufficient. Too much air, and newly formed iron may oxidize again, while the fuel burns away too quickly. The furnace had to do more than contain a fire. It had to breathe correctly. Earth and stone in the ore react with other materials and form a liquid waste called slag. The slag flows toward the bottom of the furnace, and some of it may drain away. The iron, however, does not fully melt. Tiny metal particles join together into a porous, sponge-like mass. This is called a bloom. The furnace is opened, and the glowing red bloom is removed. But the iron is not finished. Slag and pieces of charcoal remain trapped inside it, and its shape and quality are uneven. While it is still hot, the bloom is hammered. It is folded, gathered, reheated, and hammered again. Slag is squeezed out, and scattered particles of iron are consolidated into a usable material. The discovery of iron was not completed by one lucky accident. Select the ore, crush it, make the charcoal, build the furnace, maintain the airflow, remove the bloom, forge it again and again. If any one of those steps failed, useful iron did not emerge. Tiny particles of iron might form by accident in the remains of a fire. But producing one small particle once is very different from making iron repeatedly and shaping it into a tool. Even if someone found a strange black lump, the discovery would disappear unless they recognized it as iron and could recreate the conditions that made it. What mattered was the ability to notice an accident, change one condition at a time, and pass both success and failure to the next generation of metalworkers. Seen this way, the discovery of iron had 3 stages. First, find natural metal. Second, recognize that metal can emerge from ore. Third, control that process and reproduce it. Archaeology cannot recover the inventor's name, but furnace walls, tuyères, charcoal, ore, slag, and tiny flakes thrown off during forging still preserve traces of that experimentation. A lump of iron in an ancient layer is not enough to prove early smelting. Iron from a later period can move downward through holes, cracks, or channels left by roots. Finding iron ore is not enough either. It may have been carried there as pigment, building material, or a weight rather than as material for smelting. Researchers therefore study nickel, carbon, and microscopic structures inside the metal. These clues can help distinguish meteoritic iron from smelted iron and reveal the temperatures the object experienced during production. They also combine the design of the furnace, the position of its tuyère, the chemistry of its slag, and even thin scales thrown off during hammering. Then they test whether the objects, the workshop, and the dating truly belong to the same activity. The earlier and rarer the evidence, the more cautious the conclusion must be. Objects once described as the earliest smelted iron have sometimes turned out, after new analysis, to be meteoritic or to come from a different date. So who first extracted iron from ore? The honest answer is that we still cannot identify one inventor or one birthplace. In Anatolia, iron objects that may have been smelted have been reported from the early 2nd millennium BCE, but the evidence is scarce, and their dates and origins remain debated. Rare early iron objects also appear in other parts of Western Asia and the Eastern Mediterranean. We cannot always determine whether they represent the spread of one technology or several independent experiments. Iron corrodes and disappears. Early production was limited. Furnaces were sometimes broken open to remove the bloom, and later work could disturb the same site. This was a technology that often erased its own evidence. That is why the real protagonists of this story are not famous kings or named inventors. They are the unknown metal workers who stared into furnaces in many places and tried a different charge or a different flow of air from the day before. There is a famous story about iron. It says the Hittite Empire monopolized ironworking, and when the empire collapsed around 1200 BCE, its secret escaped into the surrounding world. One empire, one secret, one dramatic collapse. It is easy to remember, But current research does not support such a simple monopoly. The Hittite state may have been involved in producing, exchanging, and presenting iron as a diplomatic gift. Even so, there is no clear evidence that it produced enough iron to equip its entire army with iron weapons. Knowledge of ironworking was not sealed inside the Hittite heartland. The evidence fits better with development in several regions, moving at different speeds and following different routes. The fall of empires may have changed the movement of craftspeople and materials, but no secret door opened overnight, turning the next morning into the Iron Age. About 2,000 years separate the meteoritic beads of Gerzeh from the period when iron tools became widespread. Iron was not a magical metal that defeated bronze the moment it appeared. Early iron was inconsistent. Some pieces were too soft. Others contained more carbon and were harder, but also brittle. Even within a single tool, the material might not behave uniformly. Bronze had real advantages. It melted at a lower temperature and could be poured into molds to make complex forms. Mining, trade, casting, and repair systems for bronze already existed. Iron's advantages became greater only after the technology matured. Iron ore is available in many regions, but successful production still required good charcoal, large amounts of fuel, controlled airflow, and skilled forging. After about 1200 BCE, the use of iron increased across parts of Western Asia and the Eastern Mediterranean. But the timing and pace differed by region, and bronze and iron continued to be used together for a long time. Changing trade networks, access to raw materials, migrating craftspeople, demand for tools and weapons, and political disruption all played a role. Iron became ordinary only when technical and social conditions came together. Carbon can enter iron inside the furnace. The amount of carbon, followed by heating and cooling, can dramatically change the hardness and toughness of the material. Ancient metalworkers did not begin with modern chemical formulas. They learned from the color of the fire, the sound of the hammer, the sparks, the feel of the material, and the way a blade bent or broke. Combine a hard part with a softer one. Heat the metal, then cool it. Reheat it to reduce brittleness. Techniques like these were gradually refined in different regions and periods. Humans did not merely discover a substance called iron. They learned to control fire, air, and carbon, drawing different properties from the same basic material. So how did humans discover iron? One of the earliest confirmed encounters was with meteoritic iron that had fallen from the sky. People collected it, hammered it, and made it into special ornaments and blades. Meanwhile, craftspeople who worked with ore and fire learned to combine charcoal, furnaces, airflow, and forging. They developed a way to remove oxygen from iron ore and extract iron as a solid bloom, without ever melting the iron itself. We do not know whether meteoritic iron directly inspired smelting. The first smelting site and the first ironworker remain unknown. But if we trace the completed process backward, we can see the barriers humans overcame. They identified iron-bearing stones, created a reducing environment inside a furnace, forged the bloom into usable material, and repeated the success. No single person discovered the whole process, and it was not completed in a day. Iron technology grew from a small clue that fell from the sky. joined with generations of observation, failure, and shared knowledge. The iron surrounding us today took thousands of years to become ordinary. And before anything becomes ordinary, there is always a first trace.